Lawrence Livermore National Laboratory is a federal research facility in Livermore, California, founded by the University of California in 1952. A federally funded research and development center, it is primarily funded by the United States Department of Energy and managed and operated by Lawrence Livermore National Security, LLC, a partnership of the University of California, Bechtel, Babcock and Wilcox, URS, and Battelle Memorial Institute in affiliation with the Texas A&M University System. The laboratory was honored in 2012 by having the synthetic chemical element livermorium named after it. Background: LLNL is self-described as a premier research and development institution for science and technology applied to national security. Its principal responsibility is ensuring the safety, security and reliability of the national unregistered trademark S nuclear weapons through the application of advanced science, engineering and technology. The laboratory also applies its special expertise and multidisciplinary capabilities to preventing the proliferation and use of weapons of mass destruction, bolstering homeland security and solving other nationally important problems, including energy and environmental security, basic science and economic competitiveness. LLNL is home to many unique facilities and a number of the most powerful computer systems in the world, according to the TOP 500 list, including Blue Gene L, the world's fastest computer from 2004 until Los Alamos National Laboratory's IBM Roadrunner supercomputer surpassed it in 2008. On June 18, 2012, LLNL retook the lead on the latest edition of the list of the world unregistered trademark S Top 500 supercomputers with IBM's Sequoia, a 16.32 petaflops system packing more than 1.5 million custom power cores. It is based on the same IBM Blue Gene Q architecture used in 3 other top 10 systems which also were the most power efficient on the list. Since 1978, LLNL has received a total of 118 R&D 100 awards, including 5 in 2007. The awards are given annually by the editors of R&D magazine to the most innovative ideas of the year. The laboratory is located on a 1 square mile site at the eastern edge of Livermore. It also operates a 7,000 acres remote experimental test site, called Site 300, situated about 15 miles southeast of the main lab site. LLNL has an annual budget of about $1.5 billion and a staff of roughly 5,800 employees. Origins: LLNL was established 63 years ago in 1952 as the University of California Radiation Laboratory at Livermore, an offshoot of the existing UC Radiation Laboratory at Berkeley. It was intended to spur innovation and provide competition to the Nuclear Weapon Design Laboratory at Los Alamos in New Mexico, home of the Manhattan Project that developed the first atomic weapons. Edward Teller and Ernest Lawrence, director of the Radiation Laboratory at Berkeley, are regarded as the co-founders of the Livermore facility. The new laboratory was sited at a former naval air station of World War II. It was already home to several UC radiation laboratory projects that were too large for its location in the hills above the Berkeley campus, including one of the first experiments in the magnetic approach to confined thermonuclear reactions. About half an hour southeast of Berkeley, the Livermore site provided much greater security for classified projects than an urban university campus. Lawrence tapped 32-year-old Herbert York, a former graduate student of his, to run Livermore. Under York, the lab had 4 main programs: Project Sherwood, Project Whitney, diagnostic weapon experiments, and a basic physics program. York and the new lab embraced the Lawrence Big Science approach, tackling challenging projects with physicists, chemists, engineers, and computational scientists working together in multidisciplinary teams. Lawrence died in August 1958 and shortly after, the university's Board of Regents named both laboratories for him, as the Lawrence Radiation Laboratory. Historically, the Berkeley and Livermore laboratories have had very close relationships on research projects, business operations and staff. The Livermore Lab was established initially as a branch of the Berkeley Laboratory. The Livermore Lab was not officially severed administratively from the Berkeley Lab until 1971. To this day, in official planning documents and records, Lawrence Berkeley National Laboratory is designated as Site 100, Lawrence Livermore National Lab as Site 200, and LLNL's remote test location as Site 300. The laboratory was renamed Lawrence Livermore Laboratory in 1971. On October 1, 2007, LLNS assumed management of LLNL from the University of California, which had exclusively managed and operated the laboratory since its inception 55 years before. The laboratory was honored in 2012 by having the synthetic chemical element livermorium named after it. The LLNS takeover of the laboratory has been controversial. In May 2013, an Alameda County jury awarded over $2.7 million to 5 former laboratory employees who were among 430 employees LLNS laid off during 2008. The jury found that LLNS breached a contractual obligation to terminate the employees only for €0 or reasonable cause €0. The 5 plaintiffs also have pending age discrimination claims against LLNS, which will be heard by a different jury in a separate trial. There are 125 co-plaintiffs awaiting trial on similar claims against LLNS. The May 2008 layoff was the first layoff at the laboratory in nearly 40 years. On March 14, 2011, the city of Livermore officially expanded the city's boundaries to annex LLNL and move it within the city limits. The unanimous vote by the Livermore City Council expanded Livermore unregistered trademark southeastern boundaries to cover 15 land parcels covering 1,057 acres that comprise the LLNL site. Prior to this, the site was in an unincorporated area of Alameda County. The LLNL campus continues to be owned by the federal government. Nuclear weapons projects. From its inception, Livermore focused on innovative weapon design concepts. As a result, its first 3 nuclear tests were unsuccessful. The lab persevered and its subsequent designs proved increasingly successful. In 1957, the Livermore lab was selected to develop the warhead for the Navy's Polaris Missile. This warhead required numerous innovations to fit a nuclear warhead into the relatively small confines of the missile nosicon. During the Cold War, scores of Livermore-designed warheads entered service. These were used in missiles ranging in size from the Lance surface-to-surface tactical missile to the megaton-class Spartan anti-ballistic missile. Over the years, LLNL designed the following warheads: W-27, W-38, B-41, W-45, W-47, W-48, W-55, W-56, W-58, W-62, W-68, W-70, W-71, W-79, W-82, B-83, and W-87. The W-87 and the B-83 are the only LLNL designs still in the U.S. nuclear stockpile. With the collapse of the Soviet Union in 1991 and the end of the Cold War, the United States began a moratorium on nuclear testing and development of new nuclear weapon designs. To sustain existing warheads for the indefinite future, a science-based stockpile stewardship program was defined that emphasized the development and application of greatly improved technical capabilities to assess the safety, security, and reliability of existing nuclear warheads without the use of nuclear testing. Confidence in the performance of weapons, without nuclear testing, is maintained through an ongoing process of stockpile surveillance, assessment and certification, and refurbishment or weapon replacement. With no new designs of nuclear weapons, the warheads in the U.S. stockpile must continue to function far past their original expected lifetimes. As components and materials age, problems can arise. Stockpile life extension programs can extend system lifetimes, but they also can introduce performance uncertainties and require maintenance of outdated technologies and materials. Because there is concern that it will become increasingly difficult to maintain high confidence in the current warheads for the long term, the Department of Energy National Nuclear Security Administration initiated the Reliable Replacement Warhead Program. RRW designs could reduce uncertainties, ease maintenance demands, and enhance safety and security. In March 2007, the LLNL design was chosen for the Reliable Replacement Warhead. Since that time, Congress has not allocated funding for any further development of the RRW. The Livermore Action Group organized many mass protests, from 1981 to 1984, against nuclear weapons which were being produced by the Lawrence Livermore National Laboratory. Peace activists Ken Nightingale and Eldridge Schneider were involved. On June 22, 1982, more than 1,300 anti-nuclear protesters were arrested in a non-violent demonstration. More recently, there has been an annual protest against nuclear weapons research at Lawrence Livermore. In August 2003, 1,000 people protested at Livermore Labs against new-generation nuclear warheads. In the 2007 protest, 64 people were arrested. More than 80 people were arrested in March 2008 while protesting at the gates. 31 people were arrested in August 2013 during a protest marking the 68th anniversary of the atomic bombings of Hiroshima and Nagasaki, including famous whistleblower and author of the Pentagon Papers, Daniel Ellsberg. In the 1980s, Lawrence's widow petitioned the regents of the University of California on several occasions to remove her husband's name from the Livermore Laboratory, due to its focus on nuclear weapons. She outlived her husband by more than 44 years and died in Walnut Creek at the age of 92 in January 2003. Plutonium Research, LLNL conducts research into the properties and behavior of plutonium to learn how plutonium performs as it ages and how it behaves under high pressure. Plutonium has 7 temperature-dependent solid allotropes. Each possesses a different density and crystal structure. Alloys of plutonium are even more complex. Multiple phases can be present in a sample at any given time. Experiments are being conducted at LLNL and elsewhere to measure the structural, electrical and chemical properties of plutonium and its alloys and to determine how these materials change over time. Such measurements will enable scientists to better model and predict plutonium's long-term behavior in the aging stockpile. The LAB unregistered trademark S plutonium research is conducted in a specially designed, ultra-safe, and highly secure facility called the Superblock. Work with highly enriched uranium is also conducted here. In March 2008, the National Nuclear Security Administration presented its preferred alternative for the transformation of the national unregistered trademark S nuclear weapons complex. Under this plan, LLNL would be a center of excellence for nuclear design and engineering, a center of excellence for high explosive research and development, and a science magnet in high-energy density physics. In addition, most of his special nuclear material would be removed and consolidated at a more central, yet-to-be-named site. On September 30, 2009, the NNSA announced that about two-thirds of the special nuclear material at LLNL requiring the highest level of security protection had been removed from LLNL. The move was part of NNSA's efforts initiated in October 2006 to consolidate special nuclear material at 5 sites by 2012, with significantly reduced square footage at those sites by 2017. The federally mandated project intends to improve security and reduce security costs, and is part of NNSA's overall effort to transform the Cold War-era nuclear weapons enterprise into a 21st-century nuclear security enterprise. The original date to remove all high-security nuclear material from LLNL, based on equipment capability and capacity, was 2014. NNSA and LLNL developed a timeline to remove this material as early as possible, accelerating the target completion date to 2012. Global Security Program, the LAB unregistered trademark S work in global security aims to reduce and mitigate the dangers posed by the spread or use of weapons of mass destruction and by threats to energy and environmental security. Livermore has been working on global security and homeland security for decades, predating both the collapse of the Soviet Union in 1991 and the September 11, 2001, terrorist attacks. LLNL staff have been heavily involved in the cooperative non-proliferation programs with Russia to secure at-risk weapons materials and assist former weapons workers in developing peaceful applications and self-sustaining job opportunities for their expertise and technologies. In the mid-1990s, lab scientists began efforts to devise improved biodetection capabilities, leading to miniaturized and autonomous instruments that can detect biothreat agents in a few minutes instead of the days to weeks previously required for DNA analysis. Today, Livermore researchers address the full spectrum of threats: radiological, nuclear, chemical, biological, explosives, and cyber. They combine physical and life sciences, engineering, computations, and analysis to develop technologies that solve real-world problems. Activities are grouped into 5 programs: non-proliferation, preventing the spread of materials, technology and expertise related to weapons of mass destruction and detecting WMD proliferation activities worldwide. Domestic security, anticipating, innovating and delivering technological solutions to prevent and mitigate devastating high-leverage attacks on U.S. soil. Defense, developing and demonstrating new concepts and capabilities to help the Department of Defense prevent and deter harm to the nation, its citizens and its military forces. Intelligence, working at the intersection of science, technology and analysis to provide insight into the threats to national security posed by foreign entities. Energy and environmental security, furnishing scientific understanding and technological expertise to devise energy and environmental solutions at global, regional and local scales. Other programs, LLNL supports capabilities in a broad range of scientific and technical disciplines, applying current capabilities to existing programs and developing new science and technologies to meet future national needs. The LLNL chemistry, materials, and life science research focuses on chemical engineering, nuclear chemistry, materials science, and biology and bio-nanotechnology. Physics thrust areas include condensed matter and high-pressure physics, optical science and high-energy density physics, medical physics and biophysics, and nuclear, particle and accelerator physics. In the area of energy and environmental science, Livermore unregistered trademark emphasis is on carbon and climate, energy, water and the environment, and the National Nuclear Waste Repository. The LLNL engineering activities include micro and nanotechnology, lasers and optics, biotechnology, precision engineering, non-destructive characterization, modeling and simulation, systems and decision science, and sensors, imaging and communications. The LLNL is very strong in computer science, with thrust areas in computing applications and research, integrated computing and communication systems, and cybersecurity. Lawrence Livermore National Laboratory has worked out several energy technologies in the field of coal gasification, shale oil extraction, geothermal energy, advanced battery research, solar energy, and fusion energy. Main oil shale processing technologies worked out by the Lawrence Livermore National Laboratory are LLNL-HRS, LLNL-RISE and LLNL radiofrequency technologies. Key accomplishments: over its 60-year history, Lawrence Livermore has made many scientific and technological achievements, including critical contributions to the U.S. nuclear deterrence effort through the design of nuclear weapons to meet military requirements and, since the mid-1990s, through the Stockpile Stewardship Program, by which the safety and reliability of the enduring stockpile is ensured without underground nuclear testing. Design, construction, and operation of a series of ever larger, more powerful, and more capable laser systems, culminating in the 192-beam National Ignition Facility, completed in 2009. Advances in particle accelerator and fusion technology, including magnetic fusion, free electron lasers, accelerator mass spectrometry, and inertial confinement fusion. Breakthroughs in high-performance computing, including the development of novel concepts for massively parallel computing and the design and application of computers that can carry out hundreds of trillions of operations per second. Development of technologies and systems for detecting nuclear, radiological, chemical, biological, and explosive threats to prevent and mitigate WMD proliferation and terrorism. Development of extreme ultraviolet lithography for fabricating next-generation computer chips. First ever detection of massive compact halo objects, a suspected but previously undetected component of dark matter. Advances in genomics, biotechnology, and biodetection, including major contributions to the complete sequencing of the human genome, though the Joint Genome Institute and the development of rapid PCR technology that lies at the heart of today are unregistered trademark S most advanced DNA detection instruments. Development and operation of the National Atmospheric Release Advisory Center, which provides real-time, multi-scale modeling of hazardous materials released into the atmosphere. Development of highest-resolution global climate models and contributions to the International Panel on Climate Change which, together with former Vice President Al Gore, was awarded the 2007 Nobel Peace Prize. Co-discoverers of new super-heavy elements 113, 114, 115, 116, 117, and 118. Invention of new healthcare technologies, including a microelectrode array for construction of an artificial retina, a miniature glucose sensor for the treatment of diabetes, and a compact proton therapy system for radiation therapy. On July 17, 2009, LLNL announced that the laboratory had captured 8 A&D 100 awards, more than it had ever received in the annual competition. The previous LLNL record of 7 awards was reached 5 times in 1987, 1988, 1997, 1998 and 2006. Also known as the A-OE Oscars of Invention Euro, the awards are given each year for the development of cutting-edge scientific and engineering technologies with commercial potential. The awards raises LLNL Euro unregistered trademark S total to 129 since 1978. The winning technologies were Gemini spectrometer, artificial retina Euro restoring sight to the blind, the ROSE compiler framework, the Babel middleware, the femtoscope, a time microscope, ROSE, making compiler technology accessible to all programmers, landmine locator, eradicating the aftermath of war, laser beams centering and pointing system, spectral sentry Euro protecting high-intensity lasers from bandwidth-related damage, precision robotic assembly machine Euro for building nuclear fusion ignition targets. Unique facilities, biosecurity and nanoscience laboratory. Researchers apply advances in nanoscience to develop novel technologies for the detection, identification, and characterization of harmful biological pathogens and chemical toxins. Center for Accelerator Mass Spectrometry, LLNL Euro unregistered trademark S Center for Accelerator Mass Spectrometry develops and applies a wide range of isotopic and ion beam analytical tools used in basic research and technology development, addressing a spectrum of scientific needs important to the laboratory, the university community, and the nation. CAMS is the world Euro unregistered trademark S most versatile and productive accelerator mass spectrometry facility, performing more than 25,000 AMS measurement operations per year. High Explosives Applications Facility and Energetic Materials Center, at HEAF, teams of scientists, engineers, and technicians address nearly all aspects of high explosives, research, development and testing, material characterization, and performance and safety tests. HEAF activities support the Laboratory Euro unregistered trademark S Energetic Materials Center, a national resource for research and development of explosives, pyrotechnics, and propellants. National Atmospheric Release Advisory Center, NARAC is a national support and resource center for planning, real-time assessment, emergency response, and detailed studies of incidents involving a wide variety of hazards, including nuclear, radiological, chemical, biological, and natural atmospheric emissions. National Ignition Facility, this 192-beam, stadium-size laser system will be used to compress fusion targets to conditions required for thermonuclear burn. Experiments at NIF will study physical processes at conditions that exist only in the interior of stars and in exploding nuclear weapons. Superblock, this unique high-security facility houses modern equipment for research and engineering testing of nuclear materials and is the place where plutonium expertise is developed, nurtured, and applied. Research on highly enriched uranium also is performed here. Terascale Simulation Facility, LLNLA Euro unregistered trademark S Terascale simulation facility houses one of the world Euro unregistered trademark S most powerful computers, Sequoia. Sequoia occupied the #1 position on the top 500 list in June 2012. The current system achieves a LINPACK benchmark performance of 16.32 flops. Another Blue Gene class machine, Dawn, was installed to act as a developmental testbed for multi-petaflop computing. Titan Laser. Titan is a combined nanosecond long pulse and ultra-short pulse laser, with hundreds of joules of energy in each beam. This petawatt-class laser is used for a range of high-energy density physics experiments, including the science of fast ignition for inertial confinement fusion energy. Largest computers. Throughout its history, LLNL has been a leader in computers and scientific computing. Even before the Livermore Lab opened its doors, E.O. Lawrence and Edward Teller recognized the importance of computing and the potential of computational simulation. Their purchase of one of the first UNIV computers set the precedent for LLNLA Euro unregistered trademark S history of acquiring and exploiting the fastest and most capable supercomputers in the world. A succession of increasingly powerful and fast computers have been used at the lab over the years: 1953 Remington Rand UNIV 1, 1954 IBM 701, 1956 IBM 704, 1958 IBM 709, 1960 IBM 7090, 1960 Remington Rand LARC, 1961 IBM 7030, 1963 IBM 7094, 1963 CDC 1604, 1963 CDC 3600, 1964 CDC 6600, 1969 CDC 7600, 1974 CDC Star 100, 1978 Cray 1, 1984 Cray XMP, 1985 Cray 2, 1989 Cray Y Northern Mariana Islands, 1992 BBN Butterfly, 1994 Myco CS2, 1995 Cray C90, 1995 Cray T3D, 1996 IBM ASCI Blue Pacific, 2000 IBM ASCI White, 2004 Thunder, 2005 IBM Blue Gene L, 2005 ASC Purple, 2006 Use, 2006 RIA, 2006 Atlas, 2007 Minnows, 2012 IBM Sequoia. The November 2007 release of the 30th TOP 500 list of the 500 most powerful computer systems in the world has LLNLA Euro unregistered trademark S Blue Gene L computer in first place for the 7th consecutive time. 5 other LLNL computers are in the top 100. The November 2008 release of the TOP 500 list places the Blue Gene L supercomputer behind the Pleiades supercomputer in NASA Ames Research Center, the Jaguar supercomputer in Oak Ridge National Laboratory, and the IBM Roadrunner supercomputer in Los Alamos National Laboratory. Currently, the Blue Gene L computer can sustain 478.2 trillion operations per second, with a peak of 596.4 trillion operations per second. On June 22, 2006, researchers at LLNL announced that they had devised a scientific software application that sustained 207.3 trillion operations per second. The record performance was made at LLNL on Blue Gene L, the world's fastest supercomputer with 131,072 processors. The record was a milestone in the evolution of predictive science, a field in which researchers use supercomputers to answer questions about such subjects as materials science simulations, global warming, and reactions to natural disasters. LLNL has a long history of developing computing software and systems. Initially, there was no commercially available software, and computer manufacturers considered it the customary Euro unregistered trademark S responsibility to develop their own. Users of the early computers had to write not only the codes to solve their technical problems, but also the routines to run the machines themselves. Today, LLNL computer scientists focus on creating the highly complex physics models, visualization codes, and other unique applications tailored to specific research requirements. A great deal of software also has been written by LLNL personnel to optimize the operation and management of the computer systems, including operating system extensions such as Chaos and resource management packages such as SLURM. The Peloton procurements in late 2006 were the first in which a commercial resource management package, MOAB, was used to manage the clusters. Livermore Valley Open Campus. In August 2009, a joint venture was announced between Sandia National Laboratory's California campus and LLNL to create an open, unclassified research and development space called the Livermore Valley Open Campus. The motivation for the LVOC stems from current and future national security challenges that require increased coupling to the private sector to understand threats and deploy solutions in areas such as high-performance computing, energy and environmental security, cybersecurity, economic security, and non-proliferation. The LVOC is modeled after research and development campuses found at major industrial research parks and other U.S. Department of Energy laboratories with campus-like security, a set of business and operating rules devised to enhance and accelerate international scientific collaboration and partnerships with U.S. government agencies, industry and academia. Ultimately, the LVOC will consist of an approximately 110-acre parcel along the eastern edge of the Livermore Laboratory and Sandia sites, and will house additional conference space, collaboration facilities and a visitor center to support educational and research activities. Objectives of LVOC: enhance the two laboratories' national security missions by substantially increasing engagement with the private sector and academic community. Stay at the forefront of the science, technology and engineering fields. Ensure a quality future workforce by expanding opportunities for open engagement of the broader scientific community. Initial research areas for the LVOC: high-performance computing, cybersecurity science, Sandia's combustion research facility and transportation research, high-energy density physics, climate and energy research. The architecture of the LVOC is planned in stages. First steps including, a new high-performance computing innovation center at LLNL, open access to Sandia's combustion research facility, planning for an unclassified computing center. Sponsors: LLNL's principal sponsor is the Department of Energy National Nuclear Security Administration Office of Defense Programs, which supports its stockpile stewardship and advanced scientific computing programs. Funding to support LLNL's global security and homeland security work comes from the DOE and NSA Office of Defense Nuclear Non-Proliferation as well as the Department of Homeland Security. LLNL also receives funding from DOE Unregistered Trademark S Office of Science, Office of Civilian Radioactive Waste Management, and Office of Nuclear Energy. In addition, LLNL conducts work for others research and development for various Defense Department sponsors, other federal agencies, including NASA, Nuclear Regulatory Commission, National Institutes of Health, and Environmental Protection Agency, a number of California state agencies, and private industry. Budget: for fiscal year 2009, LLNL spent $1.497 billion on research and laboratory operations activities. Research Science Budget: National Ignition Facility $301.1 million, Nuclear Weapon Deterrent $227.2 million, Advanced Simulation and Computing $221.9 million, Non-Proliferation $152.2 million, Department of Defense $125.9 million, Basic and Applied Science $86.6 million, Homeland Security $83.9 million, Energy $22.4 million, Site Management Operations Budget, Safeguard Security $126.5 million, Facility Operations $118.2 million, Environmental Restoration $27.3 million. Directors: the LLNL Director is appointed by the Board of Governors of Lawrence Livermore National Security, LLC and reports to the Board. The Laboratory Director also serves as the President of LLNS. Over the course of its history, the following eminent scientists have served as LLNL Director: 1952 – 1958 Herbert Rourke, 1958 Euro 1960 Edward Teller, 1960 Euro 1961 Harold Brown, 1961 Euro 1965 John S. Foster, Jr., 1965 Euro 1971 Michael M. May 1971 Euro 1988 Roger E. Battelle, 1988 Euro 1994 John H. Knuckles, 1994 Euro 2002 C. Bruce Tarter, 2002 Euro 2006 Michael Anastasio, 2006 Euro 2011 George H. Miller, 2011 Euro 2013 Penrose C. Albright, 2013 Euro 2014 Brett Knapp, Acting Director, 2014 Euro President William H. Goldstein. Organization: the LLNL Director is supported by a senior executive team consisting of the Deputy Director, the Deputy Director for Science and Technology, Principal Associate Directors, and other senior executives who manage areas functions directly reporting to the Laboratory Director. The Director's Office is organized into these functional areas: Offices, Chief Information Office, Contractor Assurance and Continuous Improvement, Environment, Safety and Health, Government and External Relations, Independent Audit and Oversight, Office of General Counsel, Prime Contract Management Office, Quality Assurance Office, Security Organization, LLNS, LLC Parent Oversight Office. The laboratory is organized into 4 principal directorates, each headed by a Principal Associate Director: Global Security, Weapons and Complex Integration, National Ignition Facility and Photon Science, Operations and Business, Facilities and Infrastructure, Institutional Facilities Management, Integrated Safety Management System Project Office, Nuclear Operations, Planning and Financial Management, Staff Relations, Strategic, Human Resources Management. 3 other directorates are each headed by an associate director who reports to the LLNL Director: Computation, Engineering, Physical and Life Sciences. Corporate Management: the LLNL Director reports to the Lawrence Livermore National Security, LLC Board of Governors, a group of key scientific, academic, national security and business leaders from the LLNS partner companies that jointly own and control LLNS. The LLNS Board of Governors has a total of 16 positions, with 6 of these governors constituting an executive committee. All decisions of the board are made by the governors on the executive committee. The other governors are advisory to the executive committee and do not have voting rights. The University of California is entitled to appoint 3 governors to the executive committee, including the chair. Bechtel is also entitled to appoint 3 governors to the executive committee, including the vice chair. One of the Bechtel governors must be a representative of Babcock and Wilcox or the Washington Division of URS Corporation, who is nominated jointly by B&W and URS each year, and who must be approved and appointed by Bechtel. The executive committee has a 7th governor who is appointed by Bechtel. They are non-voting and advisory to the executive committee. The remaining board positions are known as independent governors, and are selected from among individuals, preferably of national stature, and cannot be employees or officers of the partner companies. The University of California appointed chair has tie-breaking authority over most decisions of the executive committee. The Board of Governors is the ultimate governing body of LLNS and is charged with overseeing the affairs of LLNS in its operations and management of LLNL. LLNS managers and employees who work at LLNL, up to and including the President Laboratory Director, are generally referred to as laboratory employees. All laboratory employees report directly or indirectly to the LLNS President. While most of the work performed by LLNL is funded by the federal government, laboratory employees are paid by LLNS, which is responsible for all aspects of their employment including providing health care benefits and retirement programs. Within the Board of Governors, authority resides in the Executive Committee to exercise all rights, powers, and authorities of LLNS, accepting only certain decisions that are reserved to the parent companies. The LLNS Executive Committee is free to appoint officers or other managers of LLNS and LLNL, and may delegate its authorities as it deems appropriate to such officers, employees, or other representatives of LLNS/LLNL. The Executive Committee may also retain auditors, attorneys, or other professionals as necessary. For the most part, the Executive Committee has appointed senior managers at LLNL as the primary officers of LLNS. As a practical matter, most operational decisions are delegated to the President of LLNS, who is also the Laboratory Director. The positions of President Laboratory Director and Deputy Laboratory Director are filled by joint action of the Chair and Vice Chair of the Executive Committee, with the University of California nominating the President Laboratory Director and Bechtel nominating the Deputy Laboratory Director. The current LLNS Chairman is Norman J. Patties, founder and Chairman of Westwood One, America's largest radio network, and he also currently serves on the Board of Regent of the University of California. The Vice Chairman is J. Scott Ogilvie, President of Bechtel Systems and Infrastructure, Incorporated. He serves on the Board of Directors of Bechtel Group, Incorporated and on the BGI Audit Committee. The Board of Governors uses the following committees to oversee the management and operations of LLNL by LLNS: Business and Operations, Ethics and Audit, Mission, Nominations and Compensation, Nuclear Weapons Complex Integration, Safeguards and Security, Science and Technology. See also: Center for the Advancement of Science in Spatial operates the U.S. National Laboratory on the ISS. Dielectric Wall Accelerator, Top 100 U.S. Federal Contractors, List of articles associated with nuclear issues in California. Footnotes. References: Nuclear Rights, A Weapons Laboratory at the End of the Cold War, by Hugh Gustafson, University of California Press, Berkeley, 1996, The Stockpile Stewardship and Management Program, Maintaining Confidence in the Safety and Reliability of the Enduring U.S. Nuclear Weapons Stockpile, U.S. Department of Energy, Office of Defense Programs. May 1995. Preparing for the 21st Century, 40 Years of Excellence. Lawrence Livermore National Laboratory. Report UCRLAR 108618. 1992. External links and sources: Lawrence Livermore National Laboratory, Lawrence Livermore National Security, a limited liability corporation, History of the Laboratory. LLNL. July 14, 2002. Archived from the original on October 12, 2006. Serving the nation for 50 years, 1952 to 2002. Lawrence Livermore National Laboratory, LLNL, 50 Years of Accomplishments. LLNL. 2002. UCRLA 148833. LLNL Industrial Partnerships and Commercialization, University of California Office of Laboratory Management, Society of Professionals, Scientists and Engineers, University of California LLNL Retiree Group, Annotated Bibliography for Livermore from the ALSO's Digital Library for Nuclear Issues.